We're going to finish up our worksheet number 8 is chemical reactions. We will skip worksheet number 9 and go then to worksheet number 10, which is acids, bases, and buffers. And that will help with our lab for next week. And we'll go on to worksheet number 12, equilibrium and kinetics. And I think so that's kind of the map for the rest of the quarter, which is rapidly coming to an end. So with that, I'd like to pick up with where we left off, which was page 12. We just had looked at single replacement reactions and the net ionic equation for those. And we're moving on to section 8.3, acid-base neutralizations. It's nice to get to this section because they're also a double replacement reaction. So they look a lot like precipitation reactions because they're a double replacement. And the thing that makes them sort of special is that you have an H and an OH forming a new water molecule each time. So formation of that new water molecule. So when we do that double replacement, we will have a salt and the water molecule. In this definition, the Arrhenius definition, it's convenient because we're looking at just the H coming together with the OHs. So we build that water molecule, H connected to an OH. And we will see that's the driving force for acid-base reactions. We did talk a little bit about our definition of acids, I believe in chapter 6, which is the acid produces H plus in water. So for these things, they all ionize completely. Acids tend to taste sour like citric acid and citrus fruits. They will neutralize bases, so again forming that water molecule. And they will also react with carbonates to decompose and produce CO2 gas. One of the characteristics of acids is that they turn vegetable dyes red. Litmus will turn red, and also several naturally occurring compounds, vegetable dyes, will change color with pH. And so we'll take a look at that in the buffers lab, which is next week. And that's a nice lab. It's relatively easy. The lab today is more challenging. It's more mathematical and conceptual. And then lab 8, the final lab of the quarter, is also pretty challenging. That will have a calculations-based pre-lab. Bases we can define in the Arrhenius definition. And again, that's the one that helps us build that water molecule. We will define bases then as something that releases those OH minuses in water. And they have properties that are different from acids. They tend to be slippery. Like if you feel soap and it's just slippery for a long time and you wash and it just stays on there, that's usually a basic compound. They tend to taste bitter. So alkaloids are naturally occurring basic chemicals. We see them in many medicines, but also like in the peel of a blueberry, it has a bitter flavor, and that's to protect that sweet fruit inside from insects chewing through it. So it tastes bitter. Let's see, they neutralize acids to produce that water molecule, and they have the opposite effect on those vegetable dyes. Where they turn the vegetable dyes red for acid, they turn blue for base. So again, we're going to see that in our lab, we just boil up some purple cabbage. So you are welcome to play with that at home and get some red cabbage, boil it up just a little bit. You can use the microwave and get a nice purple solution. I'm planning to show you that reaction. Okay, so when we have that acid coming together with the base, we will form the new water molecule and a salt. So here's our salt and water. So you can think about forming that new compound. One is the BX will form the salt, and the H with the OH is going to form the water molecule. So go ahead and predict the products and balance for these reactions. Remember, when you form the salt, we need to use the solubility rules to identify whether it's solid or aqueous. We need to form neutral ionic compounds for that salt. We're going to have an H plus and the Cl minus, Na plus, OH minus. We're going to recombine these, so we'll have water as a new water molecule plus our salt, NaCl, and that is aqueous. And that's all balanced. Everything's 1 to 1. So this is our typical acid-base reaction. We have a strong acid, HCl, with a strong base, sodium hydroxide, forming a new water molecule, and sodium chloride is table salt. So completely neutralize each other. All right, so on the next one, we can show those ions forming our neutral compounds. Now we have to combine these together, those ions, to make a neutral compound. We're going to write that formula with the subscripts. And we'll look it up on the solubility rules to find out if it's solid or aqueous in water. Rule number 1 says that potassium ions are soluble. So that is aqueous. And then we have to balance. We have 2 potassium. So there we have 2 H pluses, and now we have 2 OH minuses. So that means we'll have 2 water molecules formed for that reaction. So go ahead and complete and balance these reactions. In this next one, we can use the crossover method to form our neutral salt. And when we look up that salt, we find that phosphates are solid. And then we need to balance. All right, we'll take care of the balancing. Any questions on forming neutral compounds, identifying solid or aqueous, or balancing the reaction? So we have to recognize this as a polyatomic ion. So it's on our periodic table as a polyatomic ion. So that's one place to check to make sure.
Perchlorate.
Perchlorate, yes.
Okay, thank you.
Yeah, so when you start to put it together in new compounds, and it seems like a lot of different things, maybe that's a clue. Wait a second, maybe these act as a unit, as an ion. And so, I was going to say, if we have a decomposition reaction, then we will see new compounds formed in all different ways. But I won't ask you to predict them because they're very difficult to predict. We just observe what we have. It's just difficult to predict. Okay, so let's look at the net ionic equation. This is for number 2 up here, so I'll go back to purple for that one. All right, we already did this one, got it balanced. Oh, it's different, it's got a sodium instead of a potassium. Okay, so because this is aqueous, we're going to write it as ions. And there's 2 H pluses and 1 sulfate. Then for the next one, 2 sodiums and 2 hydroxides. Now we form that new water molecule. That is a neutral molecule. So that's going to stay together in our net ionic equation. And then 2 will break this one apart because it's aqueous, 2K plus, and a sulfate, SO4. All right, so now we have to cancel out our spectator ions. These are the ones that are exactly the same on both sides. So sulfate, oh, I wrote the wrong thing up here. We're looking at sodium. Na2. All right, so those are exactly the same. So they cancel out. Now everything left has a 2 in front. So we would prefer usually to have the smallest coefficients in our balanced equations. So I will just cancel out those 2's and show that the H plus comes together with the OH minus to form the new water molecule. And that's the driving force for the reaction. This is a double replacement neutralization reaction. Oh yes, the beakers are on the next page. These are so useful to see what happens, causes the reaction to proceed. So here it is. These guys come together. They give us those new water molecules. And everything else is just bumping around in solution. So double replacement neutralization. We have another kind of acid-base reaction. And these are, this one is a reaction that produces gas. It's a decomposition neutralization. And what happens for these ones is that carbonate decomposes into carbon dioxide. So this is exactly the reaction that we will be seeing today in our lab section. You can see in the picture it has that bubbling up. So we'll see that in our lab videos. All right, we're going to complete and balance. Now, if you do this like a double replacement reaction, then we would take these things and make our salt, and that stays there. That's the same. And then we would take these things, and what would those give us? What is that? Do you remember we looked at this on our solubility rules? Remember, this was a tricky one we added in. What happens with these? There they are. Right, what is that thing that we form when we do a double replacement with a carbonate in it? Do you remember, what is this called? Is it solid or aqueous? That's right, thank you. It is aqueous because it's an acid. This is carbonic acid, and carbonic acid has some unique characteristics. It's very important as a buffer in the blood. It's also very important in ocean acidification. So it's got a complex type of reaction. One of the things that it does is as soon as it's formed, if it's at regular pressure, the carbonate will bubble out. So this will immediately go to CO2 gas and water. There's that new water molecule. So these things here come from formation of the carbonic acid. So if you look at a reaction and you do a double replacement with it and you get carbonic acid, that's your clue. Wait a second, that just bubbles away. It's going to be water and CO2 in the products every time. So let's go ahead and write those. Now every time CO2 and water, and then you have to figure out that salt. And then is the salt solid or aqueous? And then we'll balance. These are all balanced differently. So remember, we have to form our neutral compounds. Use the solubility rules to identify if they're solid or aqueous. And balance. All nitrates are aqueous. And for that one, we just need 2 nitric acid. Right, we have a new water molecule because it's an acid-base reaction. We have that carbon dioxide from the breakdown of carbonate. And we have our salt. I guess we only know because sulfuric acid is a strong acid. And we're going to talk about strong and weak in the next worksheet. Okay, so we're just going to make a neutral compound with sulfate and lithium. All lithium are soluble, and then we balance. So we have 2 carbons, so we're going to need 2 of these. And for every carbonate that's formed, we're going to need 2 waters. We've got 4 H's over here, right? We've got 2 there and 2 there, and then 2 of those oxygens. CO3 is going to go to CO2, so there's 2 free oxygens. So I think that one is balanced. All right, in the next one, again, that hydrogen carbonate, if it's just a double replacement, then that will stay together as a unit. But if it's a gas evolution neutralization, then that HCO3 is going to be broken down by the strong acid. And so again, I'm just going to write water as our new water molecule and carbon dioxide, because those come from the immediate decomposition of carbonic acid. And then we have our salt, we have a strontium and a bromine, and bromides are aqueous unless they're with silver, lead, or mercury. Okay, so now we have to balance. Again, we have 2 carbons. We'll need 2 bromines, and then we've got, for H's, we've got 2 plus 2, so we'll need a 2 in front here. And then we have 2 oxygens, and that should do it. Yeah? What is MX? MX in the instruction, that's the salt. So that is this X, oh, and this M coming together to form our new salt.
Wait, we have 6 oxygens in the first half of the equation.
Oh yeah, let's take a look at oxygens. I'll do that in red. So for oxygens, we have 6. 2 times 3 equals. Here we have 2 from water and 4 from CO2.
Yeah, okay.
So when I check my balancing, I recommend that you also do this, that you keep it separate by the compounds, because it's easy to make a mistake. And so that way you can see which one. I can look, oh, did I distribute the 2? Yes, I did. Okay, good. You'll find those errors quicker if you write them as separate rather than combining them all into one number.
So, Professor, will we ever have to look at a equation and like predict what's happening, or will you always kind of tell us like, okay, this is the reaction, and then we'll know like to write the results in such and such way?
Yeah, so let me make a little list here. Usually I say that you can predict products for double replacement reactions. So that's the precipitation reactions and neutralization. Also combustion. I'll put B because that's the symbol we usually use. Combustion. What are the products in a combustion reaction? Anybody remember? Complete combustion is burning an oxygen and it produces only 2 things, CO2 and water. So that's similar. Look how similar that is. What else? What about single replacement? Single replacement can be some of the more difficult reactions, but you're still only forming ionic compounds. You're making neutral compounds out of those ions. So I tend to feel like that's a fair question because we've been working on that skill for so long to take your ionic charges and make a neutral compound. So that's really like forming a neutral ionic compound. The last one is, combination. Again, combination always just forms neutral compounds from ions. So those are the ones I will usually ask you to predict products for. Let's do a couple more. Let's just finish out this page. This has a lot of practice for classifying, which is helpful when you are predicting the products to classify so that you have an idea of what's going on in the reaction. And then we're going to do a couple where we predict the products. And, and I need to change this one. Let's make this one a sodium. We probably can't finish in 10 minutes. But let's try. Okay, so go ahead and try to find those tricks that let you balance quickly. We're going to talk about the pre-lab when we start the lab session. So we will talk about that in the lab. I would like to work together on the lab today because this one can be challenging, and I want to make sure that the scores are as high as possible and that you understand the whole purpose, right? Because it's a little bit confusing. All right, on this combustion, we have that alcohol in there. Have that oxygen there. So that can make this one tricky. This is for my oxygen line. I have 1 plus 2x. Remember that 2 allows me to solve for x, where x is the coefficient. Then on this side, we have 2 times 2 is 4 plus 3. So 1 plus 2x equals 7 minus 1. 2x equals 6. Good. X comes out to be 3. So for every 1 ethanol, this is the reaction that we saw in the last lab, burning the alcohol. It was this alcohol, ethanol. So for every 1 ethanol, it takes 3 oxygens to combust. Okay, and our last one is a single replacement. So we have a new ionic compound here. Okay, so to get the same number of nitrates on both sides, we'll have 3 of these, 2 of these, and then that's going to require my metals.